Programming models for big data. We have seen that scalable computing over the internet to achieve data parallel scalability for big data applications is now a possibility thanks to commodity clusters. Cost-effective commodity clusters, together with the advances in distributed file systems to move computation to data, provide a potential to conduct scalable big data analytics. The next thing we will talk about is how to take advantage of these infrastructure advances. What are the right programming models? A programming model is an abstraction over existing machinery or infrastructure. It is a set of abstract runtime libraries and programming languages that form a model of computation. This abstraction level can be low level, as in machine language in computers, or very high, as in high-level programming languages, for example, Java. So we can say, if the enabling infrastructure for big data analysis is distributed file systems, as we mentioned, then the programming model for big data should enable the programmability of the operations within a distributed file system. What we mean by this is being able to write computer programs that work efficiently on top of distributed file systems using big data and making it easy to cope with all the potential issues. Based on everything we discussed so far, let's describe the requirements for big data programming models. First of all, such a programming model for big data should support common big data operations, like splitting large volumes of data. This means for partitioning and placement of data in and out of computer memory, along with a model to synchronize the data sets later on. The access to data should be achieved in a fast way. It should allow task distribution to nodes within a rack, and these are potentially the data nodes we move the computation to. This means scheduling of many parallel tasks at once. It should also enable reliability of the computing and fault tolerance from failures. This means it should enable programmable replications and recovery of files when needed. It should be easily scalable to distributed nodes where the data gets produced. It should also enable adding new resources to take advantage of distributed computers in scale to more or faster data without losing performance. This is called scaling out if needed. Since there are a variety of different types of data, such as documents, graphs, tables, key values, etc., a programming model should enable operations over a particular set of these types. Not every type of data may be supported by a particular model, but the models should be optimized for at least one type. Is it getting a little complicated? It doesn't have to be. In fact, we apply similar models in our daily lives for everyday tasks. Let's look at a scenario where you might unknowingly apply this model. Imagine a peaceful Saturday afternoon. You receive a phone call from a friend. She says they will be at your house in an hour for dinner. It seems like you completely forgot that you had invited your friends for dinner. So you say you're looking forward to it and head to the kitchen. As a quick solution, you decide to cook pasta with some tomato sauce. You need to take advantage of parallelization so the dinner is ready by the time your guests arrive. That's in an hour. You call your spouse and your teenage kids to action in the kitchen. Now, you need to give them directions to start dicing the ingredients for you, but in the heat of the moment, you end up mixing the onions, tomatoes, and peppers. Instead of sorting them first, you give everyone a randomly mixed batch of different types of vegetables. They are required to use their compute powers to chop the vegetables. They need to ensure not to mix different types of veggies. When everyone is done chopping, you want to group the veggies by their types. You ask each helper to collect items of the same type, put them in a large bowl, and label this large bowl with the sum of individual bowl weights. Like tomatoes in one bowl, peppers in another, and the onions in the third bowl. In the end, you have nice large bowls with the total weight of each vegetable labeled on it. Your helpers are soon done with their work while you're focusing on coordinating their actions and other dinner tasks in the kitchen. You can start cooking your pasta. What you have just seen is an excellent example of big data modeling in action. Only, it is really the data in your kitchen processed by human processors. This scenario can be modeled by a common programming model for big data, namely MapReduce. MapReduce is a big data programming model that supports all the requirements of big data modeling we mentioned. It can model processing of large data, split computations into different independent parallel tasks, and make efficient use of large commodity clusters and distributed file systems. In addition, it abstracts out the details of parallelization, fault tolerance, data distribution, monitoring, and load balancing. As a programming model, it has been implemented in a few different big data frameworks. Next week, we will see more details on MapReduce and how its Hadoop implementation works. To summarize, programming models for big data are abstractions over distributed file systems. The desired programming models for big data should handle large volumes and varieties of data, support fault tolerance, and provide scale-out functionality. MapReduce is one of these models implemented in a variety of frameworks, including Hadoop. We will summarize the inner workings of the Hadoop implementation next week.